So this is a summary of how you can use prime factorization in all the different ways that we've seen them throughout this unit. First of all, prime factorization. Let's look at just the basic concept of prime factorization. If we start with 72, we can either use a tree diagram, long division, or cascading division to find the prime factorization. The key thing is that you are dividing out in a tree diagram factors, and you're getting them down to the smallest factors being the prime factorizations. If you're using cascading division, you need to make sure you're dividing them through by a prime. So if we do a tree diagram for 72, we can say it's 2 times 36. 36 can be split up into 6 by 6, and then we have 2 times 3 on each of those. What we want to make sure is that we find all the prime numbers and we write it as a product with exponents. So 72 would be written as 1, 2, 3 2s, so 2 to the 3, times by 1, 2, 3 squared. That would be the prime factorization for 72. Another example, if we do 240, and we divide it, say, by 10 first, and we get 24. We would then have 5 and 2, and we would have 6 by 4, and again a 3 by 2, and a 2 by 2. 240 would then have the prime factorization. Again, if we look at our 2's, we have 4 of them. 2 to the 4 times by 3 times by 5. The next examples are going to show how we can use the prime factorization to find, say, the greatest common factor or the lowest common multiple. We're going to find first the greatest common factor of 72 and 240. We've already done the prime factorization for this, so what we need to consider is looking at what is shared, what are shared factors between the two numbers. So 72, if we were to write them out, and 240, we want to find what is shared between the two. They both have a 2, both have a 2, both have a 2, they both have a 3. Those would be the product of those would be our greatest common factor. If we're looking in terms of the exponents and not the full written out format, we can actually consider what their exponents are rather than writing out the long format. Whatever is shared ends up being the lowest degree of the shared factors. So we can say that the greatest common factor is equal to 2 to the 3 times by 3, which in this case is 24. If we now want to look at the lowest common multiple of these two numbers, now we're going to be thinking about, as we multiply, and we look at all the multiples of 72, and if we look at all the multiples of 240, what's the lowest value that they share? Again, we're going to look at our factorization, and we do know that each of these have to exist, so that means that all these values have to exist in the lowest common multiple. 72 has to exist and 240, but there will be another number that actually will determine what the actual multiple is. One easy way of doing this, rather than listing out all the possible multiples of 72 and 240, is to consider their highest degree. We don't have to worry about the duplication. They both have a 2 to the 3 in both of these. They both have a 3 in both of these. But if we use the highest one, we'll get the lowest common multiple rather than if we multiply 72 by 240, which in this case is equal to 720. Another way we can look at prime factorization in terms of square root and cube roots, when we're going from an entire radical into a mixed radical, we use the property of two things being multiplied. We can actually split it up into two parts inside their own radicals. If one of these is a perfect square, we can reduce it if it's a square root. Same idea in the cubes, we'd be looking at something that's a perfect cube that can then reduce. Same property holds, except for now we're considering finding perfect cubes versus finding perfect squares. So if we look at the example of the square root of 72, we already know our prime factorization for 72, which is 2 to the 3 by 3 squared. We need to find a way of splitting this up so we can get perfect squares. Well, it's somewhat obvious that that's a perfect square because it's raised to the power of 2. But there's actually more to it than just that. So if we do an in-between step, we can split it up as 2 to the 3 times by 3 squared. 3 squared is 9, the square root of that becomes 3. The squared and the square root sign technically cross out, they cancel each other out, so we're left with just 3. Now we need to reduce this further. If we look at the square root again, it's actually the square root of 8. 8 actually has a perfect square in it. The degree of 3 is the same thing as doing 2 plus 1. So we can actually rewrite this as the square root of 2 squared times by 2 to the power of 1 by using our exponent laws. This one is a perfect square, 2 squared. So then we can write this as 3 times the square root of 2 squared times the square root of 1, or 2 to the power of 1. This reduces down to just 2, so we get 3 times 2 times the root of 2, which is the same thing as 6 root 2, which puts it into our nice mixed format. If we consider the cube root example, again, if we use our prime factorization, we have 2 to the 4 times by 3 times by 5. This time we're looking for perfect cubes. Right now, we actually don't have a perfect cube that is obvious. But again, using the property on this, 4 is equal to 3 plus 1, so we can split it up into 2 to the 3 times by 2 to the 1 times by your 3 times your 5. We can then separate the perfect cube out, which would be 2 cubed, and leave the remaining 2 times 3 times 5 inside the other radical. The cube root and the third power cancel out, and you're left with 2 cube root 2 times 6, so 30. Another thing to consider when we're working with exponent laws is that when we have something with the same base, we can either add or subtract their exponents if they're being multiplied or divided. If you're given a problem like this without a calculator, and they ask you to simplify it, as of right now the bases are all different. If we use the prime factorization of 8, which happens to be 2 to the 3, and replace it inside the bracket wherever you saw an 8, and if we replace 4 with 2 squared, and if we replace 32 with 2 to the 5, now we've created an expression that has all the same base. We can use our exponent laws to multiply your exponents, and you will get 2 to the 3x times by 2 to the 4x all over 2 to the 5x. If we look at just the numerator, when we're multiplying with the same base, we add their exponents, so you get 2 to the 7x. And when you are dividing, you subtract their exponents, so you get 2 to the 2x.